Okay, let's look at some wireless networking. Another huge section within networking is wireless, right? That's exploded over the past 20, 30 years. So let's look at some standards that help organize what we're doing on wireless. The 802 standard, IEEE, is the International Electronic something something. You can look it up. Engineers, electronic engineers, something. Anyway, they actually would meet and try to set up certain standards. That way, everybody wasn't trying to do proprietary things, because that's what happened in computers, right? I build a computer system and these disk drives work with this computer system and they won't work with the others' computer systems. It was really a problem that way. So when it came to networking, they're like, let's set up some networking standards. So as this grows, we can actually use networking. So we got IEEE 802, which stands for, they met in February. They met in February of 1980, and that's where these standards originated. That's where they started. So we got all these networking standards coming out of 802, and so when wireless came along, it was 802.11. So 802.11 is the wireless networking standards. Encryption standards also involved, they contain certain security protocols, and I don't even know why we talk about WEP anymore other than don't use it. That's what this should say. WEP was the first optional component. It was introduced in 1997, and it was erroneously called wire equivalent privacy. It's not equivalent to wired networks, and if anybody's using WEP, then they're hacked. That's just all there is to it. So this was so bad that they brought out WPA, and that was around 2003. And it was basically based on 802.11i. And what happened at the time is WPA had to come out because WEP was so trashy and you could just get your network hacked like that. It really is like 6 seconds, hack it. And so what they did was like, we can't wait for 802.11i to get ratified. So WPA came out, and then WPA2, which is where we're at now, and they have found out that there's a problem with it. So you really need to use WPA3, which is not even listed on here. But at least with WPA2, it's a lot harder to hack, and it's not like people are just going to be running around hacking it all the time. It's not as easy as the others. So WPA actually uses robust secure networks, RSN. It also uses advanced encryption standards, AES, 128-bit key, and a 48-bit key initialization vector encryption, which is more secure than the TKIP, which was used up here in WPA. Basically, what's happening is WPA has that, we get used to calling it a passphrase. People walk into your house and like, what's the password for your network, right? Because it's listed that way. That's really a passphrase. And you type in this passphrase, but that's then encrypted. And then the keys for actually keeping the data encrypted rotate in WPA2 better than they did in WPA1, and WEP didn't do it at all. That's basically how that happens. So anyway, let's take a look at frequency. If you have to realize that we're talking about Wi-Fi, that means we're talking about radio signals. Same radio signals that you listen to FM radio on, or AM radio, or the satellites communicate with the Earth with, right? These frequencies that we can't see, those are radio frequencies. So with networking, we are dealing with a couple of standards, 802.11b and G, and those both use a 2.4 gigahertz band, and I'll pull that up so you can see it. And what that 2.4 gigahertz band means is it's like a station, like 107.4, that kind of thing. This is 2.4 gigahertz, so to be what, 2,400 megahertz is what that would end up showing. And so what happens is within 2.4, you have certain non-overlapping channels, meaning that they don't cross across each other. And that's 1, 6, and 11. So there's only 3 that don't overlap. And that is meaning that there's often a fight over bandwidth because they interfere with each other. So newer protocols called N and AC, they start using the 5 gig band, which has many more non-overlapping channels. However, 5 gigahertz is much smaller, meaning that it attenuates more. So attenuation is the fact that the radio signal will fall apart as it moves away from its origin. So it becomes weaker and weaker. It is really not any different than saying, I'm going to throw this rock into the pond and I'll watch that ripple out. And those ripples will keep going, but they get smaller and smaller and smaller until it's the point that it's still happening, but you can't see that happening. And then eventually you can't see it at all. It's not happening at all. That's attenuation. So because 5 is the smaller bandwidth, it will be obstructed by obstacles much quicker. And so it attenuates much quicker. So lots of people will just go, oh yeah, we'll use 5, use 5. It's so much better, it's 5. Now that depends on your house, how far away things are in the building you're in. You could use 5 and have such a bad connection, such a low connection that, it's not helping you, that you need to use 2.4. A lot of wireless routers these days are combining all of them together, and then it figures out what's the best way to connect to you. That's what's happening. Let's actually pull up. That was stuff I had up for PowerShell in the other video. Let's pull up 802. No, we'll pull up 2.4. 2.4. Yeah, 2.4 is a fraction. There's our, this maybe will show us. We'll see if we got something good here. Let's see if we got a good graphic on here. No, just a bunch of articles. Let me pause this. I'll find one here for us. All right, boom, right there on your screen. Yeah, I figured Wikipedia's got it, right? And this will show you a good example of the non-overlapping channels and such. So within 2.4, you have actually, starting here at 2.4 and going up almost to 2.5, we actually don't go to channel 14. We usually go up to 11, 13, something like that, I think 13. In any case, see, it's actually spreading across a pretty large frequency. And so if all this is divided up into channels, like this is 14, so there's 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, right? So if you put yours on 4, then that's going to overlap on 6, meaning the data you're trying to send has some parts of the channel clear and other parts that are not. This part gets into understanding what happens when you transmit on the same frequency. You may not have experienced this. This used to be an example that I could give and everybody knew what it was. But as you're traveling down the road, if you're listening to a channel on an FM, it starts to fade out, right? It starts to get staticky. And that means basically the attenuation of that signal is it's not strong enough for your car to pick it up. Sometimes though, what you'll end up with is a pretty dang good signal going one way, and then you start moving into another signal coming from the other direction. And as you're in the middle, it keeps, one fades in and one fades out, and it keeps going back and forth. And you got the Spanish channel on there, and then you don't have it on there, and then it's back on there. That's what happens when you have overlapping channels. You're dealing with two radio stations that are transmitting on the same frequency. So even though we can't hear these, the same thing is happening when you're sending data. And that's what they mean about having non-overlapping channels. Because when you start to say, I want to send more data, we today just kind of automatically figure that there's just this magic, and we just keep pushing this magic forward. So let's look. This is B. This is old. Nobody wants to run B. That's so slow. You don't want internet on it. You don't want nothing. And these are the channels you get. But let's say that I'm actually using N. Right. So that's actually getting rid of the more details. Down here on N, and really what I end up with if I'm using N is two possible channels to use. right? This is going to use 1 through 5, and this is going to be 9 through 13. So if somebody is on G and N that's next door to me and I'm using N, right, then we're conflicting. If they're on N and I'm on N and we're both on the same channel, we're conflicting. And then that means that basically their radio signal that's coming into your house, it's making it harder for your equipment to pick up your own radio signal. That's really what overlapping channels refers to and deals with. That's why, and that's because of the frequency that happens. Now, because we use all these different channels, there is this factor of how fast we can transmit data. That's why we keep stacking up these channels. Like I said, we keep thinking that this is all magical and somehow we just get more bandwidth. Basically, what they've been doing is saying, well, we have that divided out into 13 channels. Let's actually combine these three, and these three together. Oh, let's combine these 5 together and these 5 together. And now we have more data we can send through there. Because the speed is really based on the frequency. The faster you see an up and down movement, let me actually just show you. Radio frequency, let's look at images. This is really a radio frequency here. It's showing a large spectrum, so you can see the radiation. Radiation just means that it's radiating, it doesn't mean death. And so you're dealing with this up and down. This is the frequency, the modulation of that. And the closer these get together, the closer they get together, the more data you can put on there, because the more times you see the ups and downs. So 5 gigahertz is really small, not this big. And in 2.8, I mean, at 2.4 gigahertz is about that big. So 5 to 2.4, that's what I mean. And so because of that, 5 is faster. You can encode more data on this frequency than you can on something that's slower or oscillates less, and that is your speed, maximum transfer rate. So you've got, oh, how often does this go up and down? I can encode more data along that. And oh, how many of these channels can I pack together and encode data on? So I got this big wide channel. As a matter of fact, that's exactly what they're doing with 4G to 5G. They're just taking more radio signals and jamming it in there, and now it can carry more data, because they can't really do anything about changing the frequency. Public Wi-Fi, you know what that is, if you don't read that. And then, you know, it does say, hey, don't do stuff on it because it's not secure. It's most of the time it's hacked. And an SSID, that is a service set identification. That is a strange term, but it basically comes back from, you know, the old telco days. And SSID is your wireless network name. So if you named your house, your wireless at your house McWi-Fi, then that's its SSID. That's what that refers to. And then you've got a little table that shows you your maximum transmission rates that you get with these. And most now today will let you set it all the way through here. I will say that if you've got one on your network that's transmitting as a B, then it will slow all the other devices down. That's very common. So I try not to have backward compatibility. Like if my router says, my wireless router access point switch says, hey, do you want G? I go, nope, don't want it. You know, just give me N and AC, or just AC. Most everything these days is AC. And then here's your little notes on configuring a device, a box. And there's tons of videos on there. And as a matter of fact, D-Link, Netgear, Linksys all have emulators that you can go to their sites and you can actually emulate setting up one of those boxes, which is pretty cool, pretty cool. You'll get to use a wireless network here. Oh, look at that. You get to pair Bluetooth headsets and then create a home network. So again, make sure you're doing these, looking at these demos so that you can actually go through the information on the labs really easily. It is really easy once you see the demos.